Alright guys, so in this video I'm going to teach you how to use SUVAT, the kinematics equations, in order to answer a question that's no longer just horizontal but now has some vertical to it. Okay? Now we're not looking at two-dimensional yet, we're not looking at projectiles, we're just looking at something going straight up and down. Now this should be fairly straightforward because it's very similar to what you've been doing, except in this case you always have an additional piece of information. And that piece of information, at least on the surface of the Earth, is the acceleration of gravity, because you know when you're going straight up and down that gravity is always pulling downwards on your object. The acceleration due to gravity on the surface of the Earth is about 9.81 meters per second squared. Now, in my example here today, I'm going to use 10 because 10 is pretty close to 9.81, and that way I don't have to be pulling out my calculator and make this a really boring video because I keep punching numbers in. Alright, so we're just going to work with that 10. Just make sure when you do your work, you use 9.81 or whatever else your teacher decides is the number for the day. But be careful because this only works again on the surface of Earth. If it's not Earth, if it's a different planet, if it's out in space, you may need to calculate a number for that gravitational acceleration. Alright? Okay, so with that, let's go ahead and look at the question which we have here, which is that an object is thrown vertically upwards with an initial velocity of 20 meters a second from the edge of a cliff 30 meters above sea level. Okay, so the first thing I'm going to do is I'm going to draw a picture because I'm an amazing artist. Yes, there is a cliff. Yes, there is the water. And all I know is that this object, we'll say it's a ball because balls are easy to work with, is going upwards at 20 meters per second initially. And then this distance right here is 30 meters. Okay? That's all that's given to us in the problem, other than the fact that we are assuming that this is on Earth, and therefore we know the acceleration. Okay? So, the first question here asks us to find the ball's maximum height. Now, in order to do this, what we're going to do is we're going to use the SUVAT equations. Alright? So, I'm going to make my little table, SUVAT. Okay? So, what I want is the maximum height. So I'm going to start right here where I threw the ball. That'll be my initial point. My final point will be up here at the very top of the arc before it starts to fall back down. Okay? So that's going to be my initial and my final. Right there. So the displacement, I don't know what that is, but that's what the question's about, the maximum height. So S. Okay? U is the initial velocity. It's 20 meters a second. It's 20 meters a second upwards, so I'm going to make that positive. So 20 meters per second. Okay, the final velocity. Now this is a little bit tricky. It doesn't actually explicitly say this is the final velocity, but you know what it is. Okay? If you have an object that's flying up in the air, it's going up, it's slowing down, it's slowing down, it's slowing down, so it has positive velocity all the way till it gets to the top, and then it starts falling. Now it has a negative velocity, and it starts speeding up and getting more and more and more negative. Well, what has to happen between that positive and the negative falling down? Well, at the top, it has to go from positive to negative, and when you go on a graph, when you go from positive to negative, you go through 0. Right? So at some point it has to be 0, and 0 is that maximum because it's not going any higher because it doesn't have velocity, the positive velocity anymore, but in the next instant it has negative velocity, it's going down. So we know in that instant that it has a velocity of 0. When it's right at the top, it's 0, right before it starts falling down. Acceleration we know is gravity, which I told you I was going to use as 10. Now, because gravity is pulling downwards and acceleration is a vector, I need to put the negative on there. So my acceleration is going to be negative 10 meters per second squared. Now from here I should be able to solve. I don't need time, that's not important right now. I should be able to use S, U, V, and A to solve my question. Okay, so what I'm going to do is I'm going to pull out my handy dandy formula packet, which I've got right here, and I look, and you should look in here as well. You see it? Which one do you want to use? You want to use the one that has the S, the U, the V, and the A, and not the T, which would be v squared equals u squared plus 2as. All right, so that's the one we're going to use right now. We'll go ahead and put in the numbers. We've got 0 equals 20 squared plus 2 times a, which was negative 10, times s. 20 squared is 400. I'll move it to the other side. So I got negative 400 equals negative 20s. Divide, and I have that s equals 20 meters. So there we go. It's going to go 20 meters up in the air. Done. Okay? The next part asks for the amount of time it takes to get to its maximum height. So we need the time now. This is the same point in time, going from this point where I throw it up to the maximum height. So I can continue to use this same table because it's still the same initial and final conditions. And so I'm going to use this. Now I need t. I can use any of the equations because now I've got everything except for t. So I'm going to use the one that looks the simplest, which is v equals u plus a t. Okay, so I'm going to put in v, which was my final velocity, which is 0. I'm going to put in u, which is my initial velocity, 20. And then plus a being negative 10 times t. And of course, at this point, you should be able to solve. Subtract the 20. You got negative 20 equals negative 10t. Divide by the negative 10. And you get that 2 seconds equals time. Please notice that on each of my problems, I am writing the units at the end. I didn't use it in between. The reason why is because this is all in SI. It's giving me meters. It's giving me seconds. Those are the fundamental units. Okay? That's why I'm not writing it out throughout the whole problem. But when I get to the end, I am writing that my displacement, the maximum height, is 20 meters. I am writing that the time is 2 seconds, right? You need to put those units on there so that it's understood that you know what the result is. All right? Awesome. We've done A. We've done B. We are cruising. Now we're going to move on to number 3. Now what does number 3 ask us for? Number 3 now changes the scenario a little bit, right? Number 3 says, find the time before it hits the sea. So it's no longer looking from here up to the top. We're now going from here all the way up and then all the way down until I hit the ocean. Okay? So now I'm going to need to create a new table. It's not the same starting and final conditions anymore. So I got to create a new SUVAT table. All right? So I'm going to do this one in red for you. SUVAT. Okay? Now, first is displacement. Now this time I know the displacement because I started here and I ended down in the water, right? That's what the question is. How long did it take before it hit the sea? Okay, so from here to there, my displacement is 30 meters. Negative 30 because it's down from where it started. Now, some students have a hard time with this because they say, but it went up and it went, it doesn't matter. Remember, displacement is just starting point, final point. What's the difference? The difference is 30 meters down. That's it. Okay? Everything else that happened doesn't matter. If you don't remember, go back and look at the other question and look at the part about the bee. That part. Yeah, go back and look at that. That will remind you of what's going on here. So we got a displacement of negative 30 meters from beginning to end. Okay? Initial velocity we have now is 20 meters a second, right? That was still from the problem. I'm still starting when I'm throwing it up in the air, so initial is still 20. Okay? Final velocity I don't have, and don't you dare say 0. Okay? Because a lot of students say, yeah, but it's going to hit the water. It's going, hey, stop. No. As soon as it hits the water, you have a different thing causing acceleration, right? It's changing the speed. When it's in the air, the only thing changing the speed is gravity. That's a constant acceleration. Acceleration is constantly negative 10. Okay, but if you start to look at after it hits the ground, after it hits the water, after it hits Mr. Bywater, whatever that rock or ball hits, it's now hitting another force. Yeah, there's another force. Once it does that, you're now getting a different acceleration. Remember, that's the one restriction of the SUVAT is that your acceleration must be constant. You must be able to deal with an average acceleration. All right? So what we're going to do is we're going to say we don't know the final velocity at this point in time. We can probably We don't know it right now. Acceleration, of course, is gravity. So I'm using negative 10 meters per second squared. Please remember to use whatever number your teacher asks you to. And then we don't have the time, but of course in C, that's what we're looking for, the amount of time it takes. So that's what we want. We got S, U, A, and T. So we want, again, the equation that is not going to use V. So the equation that does not use V is this snazzy one right here. S equals UT plus 1/2 AT squared. We should then be able to put the numbers in and solve. Okay? So we'll go ahead and put those numbers in. We got S, which is negative 30. We've got U, which was 20, plus 1/2 times A, which was negative 10, times T squared. So I'm going to simplify now. So negative 30 equals 20T minus 5T squared. Now I got a quadratic. Sorry, you got to deal with the quadratic. I mean, you learned how to deal with quadratics back in Algebra 1. This should be old hat, but we got to do it. So how do I solve for a quadratic? Well, I got to get the quadratic equal to 0, and then I can factor. I can use quadratic formula. I can use my calculator and do whatever I want at that point. Okay? So I'm going to move everything over to the left-hand side because I really don't like this negative right here. So I'm going to add the 5t, subtract the 20t. So I'm going to have 5t squared minus 20t minus 30 is equal to 0. To simplify, I'm going to factor out the 5. So I'm going to have 5 times, actually I'm just going to divide everything by 5. I can do that because I got a 0 over here. So divide everything by 5. So I got t squared minus 4t minus 6 equals 0. At this point, if I could factor, I would, but I can't. So I need to solve for C by using quadratic formula. So go ahead, solve for it. Let me know what you get. All right, so hopefully you had some time to work through that. You should have gotten that time equals either negative 1.2 seconds or 5.2 seconds. Now you got to kind of think through this because one of those doesn't really make sense. Okay? Remember what you did is you just solved a quadratic. You solved a quadratic for when the ball would reach 0 down here at the ground. Okay? Now, if you were to draw the parabola here and it would continue back this way, you would actually get 2, right? One of those before you threw the ball, assuming that the ball kept the same speed, acceleration, everything else from the ground. That one doesn't really make sense because the ball did never start there. So the negative time, we should just get rid of. It doesn't make much sense in this situation. So we take out that one. We're left with 5.2 seconds. 5.2 seconds is the amount of time it takes to get all the way up to the top and then all the way back down to the water. Okay? Now, a side note, you could have done this differently. We already know from the first part that it takes 2 seconds to get up to the top. It will take 2 seconds to get back to this point in time. So there we've got 4 seconds. So from that point, all you would need to do is say, well, how much time does it take to get from here down there? And so you could do a SUVAT table, and you could work through that and find out the amount of time it would take for that section right there. Okay? You could do that. It would give you add it on to the 4 seconds, and it would give you the same answer. Okay? All right, so that's C. C is the time before it hits the sea. Done. Now we're up to the speed with which it hits the sea. Now, of course, to answer that, we're going to be able to stay with the same table because we're still starting where we're throwing it up. We're ending where it hits the ground. I don't need to do up and then down. I just do beginning and end. Okay, that's the beauty of the SUVAT. That's the beauty of vectors is that we just pay attention to beginning and end. So I want to find V now. So again, I can use any equation. Okay, any equation is fine because I now have time as well, which was 5.2 seconds. Again, I think I'm just going to go with the easiest one I got there, which is that V equals U plus AT. V is what I'm looking for. U is 20 plus A is negative 10 times T, which was 5.2. Negative 10 times 5.2 would be negative 52. So plus negative 52. Add those together, I get a final velocity of negative 32 meters per second. And you say, but negative, that don't make any sense. Of course it makes sense. The negative on velocity is what? It's the direction. It means that it's traveling down, which, yes, it is traveling down when it hits the water, isn't it? So therefore, we've got a velocity of 32 meters per second downwards, or negative 32 meters per second. All right, so check. The last question is, what is the total distance traveled by the object? You already have all the information you need, right? How high did it go when it went up to its top point? We know that. We solved that. That was here. The top height was 20 meters, so it went up 20 meters. Okay? And then it went from there back to the beginning, 20 meters. And then from there, it went all the way down to the bottom, which is 30 meters. We're done. 20, 20, 30 adds up to 70 meters. And so the answer to the final question is 70 meters. That just takes a little bit of thinking and being able to break it up piece by piece. Notice that it is the total distance. Distance is affected by the path, whereas displacement is only negative 30, as we've discussed before. All right, hopefully that's helpful. Hopefully that ran you through a couple of different situations where you could use SUVAT with a vertically moving object, and hopefully that's enough to get you moving. See you next time.